So this one's a little bit tougher because it's not about like the shadow changing. It's about that angle of elevation changing. All right, which we have never even talked about yet. So maybe you saw this and like, what? But the set, I didn't even read that is not a good thing to hear right now. All right. Oh my. All right. So look, here's what we know. We know that this man is 6 feet tall. We know that he's walking for some reason towards a wall, and the light that is behind him is 40 feet away. Okay? We also know that as he walks, right? That as he walks, this length right here is changing. Now we're really interested when that is 10, because then this over here would be 30. But since they're changing, we write them out in terms of variables, x and 40 minus x. Remember, never put a number in if it's changing until after you derive it. Okay? And usually what we usually do is put this up here as h as shadow, but we don't even care about that right now. That's not even the question. The question is how fast is the angle of elevation changing? So we got to put the angle of elevation in here. And remember, the angle of elevation is always the angle up from the horizontal to the top of something. So the angle of elevation is right here where the light is. We good with that? Okay. What's up? Yeah. Okay. So then, again, if you're confused by this, you gotta start thinking, what rate of change do I know? Because they're definitely asking you for a rate of change. When you see the words "how fast," they want a rate of change. Okay. They want to know how fast the angle is changing. How can I write that symbolically? If we call the angle theta, then the rate of change of theta. Oh, man, that's so nice. We want d theta dt. It is true. I want to know what that is. That's our goal. All right? So if you're asked for a rate of change, they probably gave you another rate of change to compare it, like a related rate. All right? And they're telling us that the man's walking at 4 feet per second. So, Timothy, what rate of change would that be? How would I write that? If he's walking at 4 feet per second. Yes, sir. And it's positive 4 or negative 4? It is positive 4 because it's growing. Cool. So if we know how fast x is changing, what's wrong? If we know how fast x is changing and we want to know how fast theta is changing, then we need an equation that links x to theta. Okay? Because theta is an angle and x is the side of a triangle, this is going to be a trigonometric equation. All right? Oh my gosh, trigonometric. It's so fun. Say it. Say it, Amitash. Trigonometric. It's so good. Okay? What equation will link x and theta? Look at our triangle. What's Seneca? Yeah, tangent of theta is what? Tangent of theta is 6 over x. Again, you just need an equation that has an x and a theta in it, and we're going to derive it. Now, I'm going to make one small suggestion here. Because when we derive this, we have the x is in the denominator, so we're going to get negative 6 over x squared dx dt. If we could get x into the numerator and then derive it, that'd be like instead of 6 over x, if we wrote it as x over 6, that'd be easier to derive and be a little bit less work. So cotan, yeah. Okay? Now, you do not have to do that. You can do tangent of theta and it will work out. Again, it doesn't matter which equation you use, you just need an x and a theta in it. This was just a little bit simpler when we derive it. But you got to remember what the derivative of cotangent is. The derivative of cotangent, Sophia, do you know this? No. Negative cosecant squared theta times d theta dt. Because we got to derive the inside part. So I think a common mistake on a question like this is to forget that d theta dt. But then what's going to happen is when you try to plug in things, you're not going to have a d theta dt to solve for. So you're going to know something's wrong. All right? And when we derive the right-hand side, you're going to get 1/6 dx dt. Okay? And now we just plug in everything we know. Remember we said dx dt was 4 because it was x over 6. Right? You okay with that? Like x over 6 is the same exact thing as 1/6 x. So the 1/6 is just kind of hanging out there, and you derive x and get dx dt. All right? We're not supposed to know d theta dt. And then the little wrinkle that pops up here is, like Sophia's saying, I don't have a calculator. How am I supposed to know what cosecant is? All right, so the thing is, we don't need to know what theta is. We need to know what cosecant of theta is. And in a right triangle, cosecant is just the ratio of two sides. Like sine is opposite over hypotenuse, tangent was opposite over adjacent, right? Cosecant's just a side over a side. You just got to pick the right sides. Okay? Do you remember sine? It's not opposite over adjacent. Sine of theta was opposite over hypotenuse, right? And cosecant is the reciprocal of sine. So it's the hypotenuse over the opposite side of theta. Okay? It's just a ratio. We use a calculator most of the time because we don't have right triangles and because we look at sine as a function that goes past 90 degrees. Okay? But in a right triangle, that's all cosecant is. It's the hypotenuse divided by the opposite side. So if we come back up to our triangle, do we know the hypotenuse right now? No, we don't. Do we know the opposite side? It's 6. Okay? But we need to know the hypotenuse. And anytime you need to know one side of a right triangle, there's only two ways to do that. Through trig or Pythagorean theorem. Okay? We know at the point in time that we care about, x is 10. Right? Because he's 30 feet from the wall. So by the Pythagorean theorem, we get 100 plus 36. So the hypotenuse is square root 136. Which means the cosecant of this angle is the square root of 136 divided by 6. And then we're squaring it when we plug it in. So cosecant squared is 136 over 36, and it's negative. Because it was negative cosecant squared. Because it's squared. We're squaring it. What's up? We're good?
Wait, so when you do that, you square both the numbers you plug in?
Yeah, the square of a fraction is just square top and bottom. Square numerator, square denominator.
Fraction, but it was square root of 136.
It was a square root of 136, but we're squaring it.
So it's just 136, right?
Hey, man.
It's really 36.
Because it was 6 in the denominator.
Oh.
Okay? Everybody with me? I'm just plugging in a fraction, we're squaring it, which squares the numerator, squares the denominator. And it's negative because it was negative cosecant squared. And now look, this is just an algebra equation. D theta dt has to be 4 times a sixth over here, by the way, is 2/3. And then we got to multiply by the reciprocal, so it's going to be negative 36 over 136. How nice is that? It's very nice, I'll tell you. That's how nice it is. Okay? And then we just got to, this is multiplication in here. We should write it like this, I guess. We can cancel things out. How many times 3 go into 36? 12. So that's negative 12. Cool. We also know 4. We can cancel out a 2. So 2 becomes a 1. 136 becomes a 68. Then we cancel out another 2, right? So the 12 is going to become a 6. And this is going to become a 34. And we cancel out another 2. This is 17, and this is negative 3. That's all we can do. So it's negative 3 over 17. And then we need units on this. So look, it's going to be something over something, right? So what are angles measured in? In calculus? Radians. They're radians. No. What? No, just radians per...
Second.
Well, yeah, what's seconds, yeah. Yeah, man, rad per second. All right, and again, because the reason why it's not degrees, and we never really say this in a calc class, but the derivative of sine is cosine, but not when you measure in in degrees. If you measure in degrees, you don't get cosine when you derive sine. You get something a little bit different. Okay, so that's why we always measure in radians in here. It ends up being the chain rule, because you got to, to convert it, it stretches it out. So you'd have to multiply by the conversion for 180 over pi, or pi over 180. I don't know. But anyway, you end up getting a chain rule. So it is sine, but then you got to multiply by another number out front of it. All right? So it's always radians per second or minute or hour, depending on the unit of time when we do